Sure. I mean, a neutron star is a stellar remnant. It's the end stage of stellar evolution. So when you're looking at stars that are, generally speaking, 3, 4 times the mass of our sun or larger, they end up their lives as either a neutron star or indeed potentially a black hole. It's mass dependent. Stars like our own sun, a couple of times the mass of our sun, they're going to end up creating what we call white dwarfs. But once you go further up the mass scale for stars, the more massive the star, the more, shall I say, titanic is their death throes. So when we're talking about stars with sufficient mass, as I said, at least 4 times the mass of our sun, we're talking about stars that end their lives in a supernova explosion. That leaves behind a stellar remnant. And again, depending upon mass, we're talking about leaving behind either a neutron star or a black hole. Now, you can create neutron stars and black holes in other ways with white dwarfs that end up creating too much mass, tripping over the Chandrasekhar limit, and so on. But generally speaking, we're talking about these objects, which are only a few tens of kilometers in diameter, very, very compact with enormous densities. What has happened there is that the mass that is left over in the cores of these dying stars, or in the case of a white dwarf that accretes too much mass, there is now so much matter that the gravitational force literally overwhelms regular matter, which of course is atoms, protons, neutrons, and electrons. And the compaction is so fierce, pulling in so tightly that literally the atom becomes a ball of neutrons. When you're talking about such phenomenal gravitational pull, the only type of object that is going to be able to resist further that compaction process is a sphere, where all points are equally distant from the surface, so that there is no atypical or asymmetric gravitational pull. So you've got this ball of material that starts out being a few tens of thousands of kilometers in size, but the mass has generated such a gravitational pull that it overwhelms matter in the regular atomic format, crushes them to become basically neutrons, and it keeps compacting down until it can compact no more. What we call neutron degeneracy rules, and that generally ends up being an object that is a few tens of kilometers in diameter. And as I said, the only object that can result from that level of gravitational compaction is a sphere. And it's rotating courtesy of the conservation of angular momentum. All stars are rotating. Even our own sun is rotating. Does it about once every 25 to 30 days. It's a pretty slow kind of guy. But nonetheless, it's 1.5 million, 1.4 million kilometers in diameter. If you now sort of shed most of that matter and compact the core, angular momentum must be retained. And so smaller radius for a higher mass ends up with a faster rotation rate. Mm-hmm. So take 1.4 million kilometer sphere spinning, bring it down to say 30, 40, 50 kilometers, do the math, you're talking about a phenomenal increase in spin rate associated with the neutron star.
Because
of course, it's not a star.
Yeah. Because I'm also assuming like any asymmetries in the actual star would simply be pulled in by gravity, right? So like it would kind of like balance out that way. Like that's actually pretty interesting.
That's right. And, well, you might have heard of again, it's a bit of a misnomer, a starquake. Some neutron stars do change their rotation rate ever so subtly, and we think it's associated with their sort of surfaces cracking a little bit and the rearrangement, if you will, to get rid of that crack, so as to speak. So the change in rotation rate is associated with some type of deformation that may have taken place on the surface.